Understanding Dam Maintenance and Repair with Corey Clark from the New Hampshire Department of Environmental Services. And before we get into that, I'm going to give you a few quick housekeeping items before we start. So if you just heard, we're going to be recording this session. So you can go back and watch or send it to your friends and neighbors. It'll also be shared on our website and also our YouTube channel. And we ask that you also keep yourself muted with your cameras off for the duration of the webinar. And this is just to allow Corey the space to present, reduce distractions from noises in the background and others' videos. And if you have any questions that come up during the presentation, please share them in the chat box that we've already talked about. There should be a little icon down on the bottom that says chat. It looks like a little chat bubble. And if you cannot see that, there's a little circle that has 3 little dots in it that says more. Go ahead and click that, and there should be an option for you to add that chat bubble to your bottom panel. And we'll save those questions until the end for Corey as they come in, and then we'll spend some time at the end going through those questions. After this webinar, you're going to receive an evaluation form, and we absolutely want you to let us know how we did and if you have ideas for future topics. We'll share that feedback with Corey too if you have anything that you'd like to share about the presentation. So, just as a reminder, or in case you're new to us, we're New Hampshire Lakes. We're a nonprofit organization that's the voice of all of New Hampshire's lakes, with a mission to restore and preserve all of our lakes in New Hampshire. We have 3 primary programs that we focus on at New Hampshire Lakes. Our advocacy program, which will be ramping up in the next couple months as the 2027 season starts. We have our conservation programs, which includes our Lake Coast Courtesy Boat Inspection Program, our Lake Smart Lake Friendly Living Program. Both of those are heading into their last stretch of the summer. Very, very busy for us. And then, of course, we have our outreach program, which is bringing you this webinar tonight. We have so much going on throughout the whole year, and if you have any questions or are interested in about those programs, please let us know. Feel free to reach out to us to learn more. And you can also support all of these great programs by becoming a supporter. You can join this big community in New Hampshire that love and care for our lakes. And as you didn't already guess, we're your hosts for the evening, New Hampshire Lakes. I'm Bria Arvidsson. I'm the Director of Programs at New Hampshire Lakes. And I have with me Andrea Lamoureux, who is joining as our co-host. She's our fierce leader and President and Policy Advocate at New Hampshire Lakes. And you're here not to listen to me, but to listen to Corey Clark, our expert presenter this evening. He is the Chief Engineer at the Dam Bureau at New Hampshire Department of Environmental Services. And Corey is extremely knowledgeable about dams we have in New Hampshire, and we could not be more excited and happy that he's here and can join us tonight. And so without further ado, I'm going to stop sharing my screen and turn it over to Corey so that you can learn about dams.
All right. Can everybody see that? See that all right?
Yep.
Excellent. Excellent. All right. Well, thank you for having me here tonight. Once again, my name is Corey Clark. I am the Chief Engineer at the Dam Bureau at the New Hampshire Department of Environmental Services. And really kind of just going through what exactly we do here at the Dam Bureau and then diving into how we go about some major repair projects that we have, decisions that have to be made throughout the process, but really keeping in mind that while this is certainly being taken from a state perspective, this is the same process that any dam owner would have to go through, whether it's a privately owned dam, publicly owned dam, or a municipality owned dam. So kind of kicking things off, one of my favorite lakes, I don't know if it's the favorite, but certainly Lake Francis up in Pittsburgh, New Hampshire, just because of the viewscape from up on Murphy Dam. This is actually the intake tower on Lake Francis for Murphy Dam. And so that's certainly one of my go-tos. And I certainly enjoy walking across the crest of that dam anytime I'm up there. So what exactly is a dam? Um, Here in the state of New Hampshire, a dam is really anything over 6 feet in height. There are some nuances because of stormwater detention basins and also lagoons that hold different types of septage or other waste, but really it's a man-made structure that's over 6 feet in height or more. The other nuance being if it's located on the outlet of a great pond. And so here in New Hampshire, there's roughly 1,000 different lakes that are over 10 acres in size in their natural state. Those are great ponds. And so regardless of the height of the dam on those outlets, they are certainly all fall within RSA 42.2, which are defined as dams. Now, breaking that down a little bit more, you're going to hear a lot throughout this presentation on different hazard classifications. So here in New Hampshire, starting things off, we have a high hazard dam. Those are dams that if they were to fail, there'd be probable loss of life. Now, you can certainly have a brand new high hazard dam, meets all the criteria, as safe as can be. It's still a high hazard dam because if that dam was to fail, there'd be probable loss of life. Moving things down a little bit, we have significant hazard dams. Those are dams, if they were to fail, there would likely not be loss of life. However, there'd be major economic damage, such as a state route actually being impacted as a result of that failure. Then we have low hazard dams. Those are dams that if they were to fail, there'd be loss, typically like a town road, maybe some private property damage, but really not impacting any structures. And then the bulk of the dams in the state are actually what we call non-menace dams. Those are dams, if they were going to fail, the theory being nobody would really know except for the dam owner. There wouldn't be any loss of life. There certainly wouldn't be any property damage or other impacts. So going back to the question that was on the first slide while we were getting the introduction. So there are over 5,000 dam records in the state. So those are all the different records from dams that were built previously that are no longer there. There are many sites throughout the state that at one time or another had a dam, typically a wooden timber crib dam in the 1800s. If you go to those sites today, there's nothing remaining of that prior dam being there. So we have records that actually go back to the 1930s and some records actually prior to that. And so all those records combined lead to the 5,251 dam records. However, how many are active dams? These are the dams that are over 6 feet in height or located on a great pond or maybe a stormwater detention basin. Roughly 2,596 dams are all located throughout the state, and those are our active sites. So those make up the different hazard classes, which I'll get to in a moment, and also the non-menace dams. And so those hazardous dams, those are the ones being high, significant, and low. There are 814 hazardous dams. And I'll jump into it a little bit more in a minute, but those are the dams that get inspected on routine basis. Basically, if those dams fail, there would be impacts, whether it's loss of life or even loss of a town road. And so those are dams that we classify as hazardous and are inspected. Breaking that down a little bit more, there are 179 high hazard dams in the state. There are 131 significant hazard dams in the state, and there are 503 low hazard dams in the state. So certainly you can see that as you move down from that high hazard classification, moving down, with the exception of significant hazard dams, really you start seeing more and more numbers because the vast majority of dams are either in a remote location, they're on a water body that's typically pretty small in size, and so the impacts from those failures aren't widespread. Hence also why you see so many non-menace dams, almost 1,800 non-menace dams, which are actually not shown on the map, just for clarity purposes. Now we dive into what we call the condition of the dams. And so they're actually broken down, and this is where you can kind of get into, is my dam in good shape or is my dam in bad shape? And so out of all the different dams we have in the state, these are the hazardous ones. So those are 850 dams. 251 are satisfactory. They meet all the different loading conditions. They're designed properly and can handle the different storm events that are applied to the dams. And then we have 223 fair dams. So those are dams that might have some concrete deterioration, but really they still meet all the loading conditions. They still can pass the design storm event, but there are some issues that may need to be addressed. And then we have 205 poor condition dams. And those are dams that don't meet a loading criteria. So think of it this way. Think of it as a bridge that may have some sort of deficiency in which it's not meeting the actual design load for the bridge. Similar for a dam. So that's 205 dams that either don't meet stability criteria during a flooding event or can't pass the required discharge during a flooding event. So going back to high hazard dams, for example, those dams have to pass the 1,000-year storm event with 1 foot of freeboard. Significant hazard dams have to pass the 100-year event, and low hazard dams have to pass the 50-year event. So if those dams cannot pass that volume of water through a spillway or other means, then that's where they get shifted into the poor criteria. And then unfortunately, we do have some unsatisfactory dams. Those are dams that are deemed unsafe. And most of those 6 dams throughout the state are actually in a lower state. So the water level has actually been reduced behind that dam to make sure the risk isn't too great to those downstream. So I apologize that things got moved around a little bit in this slide, but the purpose of the dam. So we have most of the dams in the state, roughly over 40% are for recreational purposes. Another 27% are for conservation. And then we kind of dive into the other different uses. So we have mill uses, hydro makes up about 2%. And most hydros in the state are regulated by FERC, so actually regulated by the feds. There are some other hydros that are non-FERC regulated because they're grandfathered in. They were generating power prior to the passage of the FERC criteria in the 1920s. And then we have water supply and a couple other means. But really, most of the dams in the state are actually there for recreational purposes. So who are actually the owners of the dams in the state? Now, the state of New Hampshire owns a lot of dams. You're going to hear about that in a minute here. But really, the bulk of the dams in the state are privately owned. And so that really is because the bulk of the dams that we see are those non-menace dams. And most non-menace dams are owned privately. So there might be a farm pond dam that was built, say, in the 1960s. It could also be a dam where they built a driveway and they wanted to have some kind of pond alongside their driveway. Still meets the criteria of a dam. Once again, it's a non-hazard, non-menace dam. But then we break down into municipal owned dams, state owned dams, and then federally owned dams. Those federally owned dams, those are typically the big flood control sites that everybody's familiar with. The Hopkinton Everett Dam over in Henniker and Ware. Then we have the Franklin Falls Dam up on the Pemmy. And then we have the Blackwater Dam, the Edward McDowell Dam, and a few others scattered throughout. But the federally owned dams, those are typically the big Army Corps of Engineers flood control facilities. So the Dam Bureau is actually broken down into 3 sections that I oversee. And so I'll go through each section, but all those sections together really create the Dam Bureau. And so as you're out paddling on these bodies of water, enjoying these bodies of water, you may see, one or more different individuals from the Dam Bureau, particularly trying to either do operations at a site on a lake, or doing inspections, or even reconstruction. So the dam safety and inspection section. These are the men and women that are responsible for all those active dams. So roughly the 2,600 dams all throughout the state. Those are the 850 hazardous ones, along with all those other non-menace ones. So they do routine inspections on the hazardous ones. High hazards get inspected every 2 years. Significant hazards get inspected every 4 years. And low hazards get inspected every 6 years. All the non-menace dams typically don't have routine inspections. However, they are still in our database, still part of that active structure. So if there's ever a time in which one of those dams get reconstructed, or if an issue comes up at one of those dams, our dam safety personnel can respond accordingly. So we work with dam owners to ensure their dams are safe, but we also work with the AG's office on enforcement actions. So if there's a dam out there that either its owner has gone bankrupt, there's a delinquent dam owner, we work with the Attorney General's office to make sure that those dams aren't creating a hazard or a risk because they're not being maintained properly. Like I said earlier, we actually work with the Federal Energy Regulatory Commission on overseeing hydropower dams. Hydropower dams are regulated by FERC. However, we have an active role in participating with FERC because if that federal license to generate hydropower ever goes away, the regulatory oversight for that particular dam now falls on us at the state. Now we move into the operation and maintenance section of the Dam Bureau. These men and women are responsible for operating 202 dams throughout the state. Those are primarily dams owned by NHDES and also New Hampshire Fish and Game. It also includes doing operations at all the big lakes for the most part throughout the state. So we own the dams at the outlet of Lake Winnipesaukee, Winnisquam, Squam, Newfound, Lake Sunapee, Lake Ossipee, and many of the other different lakes all throughout the state. With that being said, trying to monitor that inventory of dams and the inventory of lakes and what's going on at those lakes, we actually have a website that anybody can go to and see what's happening on over 30 different water bodies throughout the state. We also have a cooperative stream gauging agreement with USGS in which we help fund different stream gauges throughout the state. So not only do we have data on a lot of the lakes in the state, particularly the big ones, but we also have data on a fair amount of the different streams and major rivers throughout the state as well. And so anybody can go on and see what's happening there. As shown in that photo, we also collect precipitation data. We also collect temperature data and some other parameters at some of the sites. That data is then used internally to help with forecasting and figuring out what's going to happen on these different water bodies with different rainfall events or even flooding events coming down the line. We do have 8 leases with hydropower entities. So we have 8 dams that can generate hydro, and we don't actually operate those ourselves. We actually lease those sites out to private hydropower operators. We also have water user agreements. So you'll hear more about this later in the presentation. But these water user agreements, basically downstream entities, typically hydropower entities, actually pay for the portion of the water actually being released from different water bodies. So say out of Lake Winnipesaukee, those hydropower entities that are down on the Winnipesaukee River and down on the Merrimack River pay for the benefit of having that water being released. Then we move on to the engineering construction section, which is responsible for 270 dams all throughout the state. So this also includes dams that are owned by other agencies. Department of Natural and Cultural Resources, Department of Transportation, UNH, Veterans Home, and a few other agencies as well. So that group is responsible for all major repairs, both in-house and out-of-house. We are fortunate that we do have our own in-house construction crew. You can see them in this photo right here. This is the crew working on a high hazard dam that's owned by Fish and Game, Copps Pond Dam up in Tuftonboro, New Hampshire, that was recently reconstructed. And with that, we also have to manage all the different emergency action plans that go along with all these significant and high hazard dams. And so for Copps Pond Dam, you can see this is a typical example of basically the mapping that goes with an inundation plan that's a part of an emergency action plan, in which you can see different portions such as Route 109 and other structures that would be impacted as a result of the failure of that dam. So how do we go about funding all this? Well, there are challenges certainly to be said. So the state owns 64 high hazard dams. A recent analysis in 2023 estimated that cost to rehab all the 64 high hazard dams would be on the ballpark of about $300 million. The 34 significant hazard dams would be about 54 million. The 80 low hazard dams would be another 54 million. And the 97 non-menace dams would be about 6 million. Certainly the criteria, as I mentioned earlier, a high hazard dam has to pass the 1,000-year event, whereas a low hazard dam only has to pass the 50-year event. It's much easier to meet that criteria for low hazard dams. Therefore, the cost and the design implications are much lower than, say, for a high hazard dam. However, the total cost of all this together is almost $500 million here just in the state of New Hampshire for state-owned dams. So we run currently on about a budget of about 7.5 million annually. About 70% of that is state funded through state general funds and capital funds. And then we do what we can to try to allocate additional funding through federal entities, such as through FEMA, through the National Dam Safety Program, that actually helps fund our dam safety inspectors. And then we're also looking into trying to collect other federal grants through FEMA, such as the High Hazard Potential Dam Grant Program. That's a program in which not only state dams have been rehabilitated, but also privately and municipally owned dams as well. So, however, to bring all the dams that are owned by the state into compliance, we would probably need to double that allocation to roughly about 16 million annually to try to bring all those different dams up to current standards. And once again, this is not just a state challenge, but this is also the same challenge that private and municipalities have with trying to fund their dam reconstruction projects. So some of the challenges and why are we seeing the cost continuing to go up? The average age of state-owned dams is well over 100 years, and it's really not that much different for dams all throughout the state. Is a lot of these dams were built for downstream mill purposes by private entities. So they are originally built in either the 1800s or the early 1900s. These photos here are from Goose Pond Dam. You're going to hear more about that in a minute. But these dams were built for those purposes. However, as the need for water power decreased, the ownership transferred from these private entities to either the state or public entities as well. The other thing that's happening is there's just a lot more development going on, particularly downstream of dams within different floodplains. This is just one example of the homes located within the FEMA flood map downstream of Ossipee Lake Dam that we own and operate as well. So one thing I like to point out is the number of high hazard dams, once again, not just for state, but also private and publicly owned dams, is continuing to go up. And it's not because new high hazard dams are being built, it's just these what were once low hazard dams now have a home or multiple homes built downstream of them. Now that low hazard dam is being reclassified as a high hazard dam because if it failed, it would impact those homes. Therefore, the criteria increases for that particular structure. So for one example, in 2004, there were roughly 30 state-owned high hazard dams. Now there are 64 high hazard dams. The modeling has gotten much, much better. This is computer-aided modeling, not only trying to figure out what's going to happen in a watershed when water is applied to it, but also trying to figure out, are these dams stable or not? And so when you're using those new modeling techniques to really break down and analyze structures, we're finding that a lot of the structures aren't meeting the criteria. So for this example, these are 3 high hazard dams owned by Fish and Game. None of those structures on the Merrimack River actually meet the discharge capacity. And a couple of those structures actually are deficient in stability as well. So those are issues that need to be addressed. One option that we always look into is trying to actually decide, is it in the best interest to actually keep this dam, or can we remove this dam? So for example, these are 3 state-owned dams on the Piscataquag River over in Goffstown and Manchester. At one time, they all produced power. Now, the only dam that produces power is Greg's Falls Dam. Hadley Falls Dam hasn't produced since 2007, and Kelly's Falls Dam, unfortunately, due to regulatory requirements for hydro, the hydropower leasee actually walked away from that site in 2024. So now we're left just producing power at Greg's. Knowing that we're going to have to rehab all of these sites eventually, we're actually pursuing removal at Hadley Falls Dam. But it is a challenge. That dam in particular is in the central Main Street area of Goffstown. So there are going to be impacts as a result of that dam removal. So let's jump into Goose Pond Dam to really kind of, how do we make decisions about dams, and really how do we go about doing these reconstruction projects that some of you may be familiar with, some of you may not be familiar with. This is a dam that's located up in Canaan and Hanover, up in the Upper Valley. It's part of the Mascoma River watershed. It's roughly 31 feet tall. It's a little over 1,200 feet long. And the water body is relatively small. The drainage area is relatively small, but the dam itself is actually a pretty good sized dam here in the state of New Hampshire. Once again, a high hazard dam. It was constructed in 1918 for water storage for downstream mill purposes. It was designed as an earth dam with a concrete core wall that you can see here on the right of the screen. So this is the concrete core wall over here. And actually, one interesting thing in this box, there was a former wooden dam here from the late 1800s as well. So this dam was much, much bigger, took place to that original dam that was built in the late 17 or 1800s. However, one of the things we try to hone into is try to figure out the history of these dams. And like I said, fortunately, our records go back to the early 1900s and sometimes into the 1800s. So with that being said, understanding what's happened at a dam in the past, not only with the construction, but what issues have been in the past, help drive rehabilitation and decisions moving forward. One thing I do want you to keep in mind is this actually red barn that you see here on the right of this photo. This is taken in 1928 when they discovered some seepage, basically water moving through the dam. And so they actually put in a foundation drain along the bottom of the dam to help collect that water that was moving through the dam at the time. 1952, they actually did a lot of different modifications to the outlet structure to try to move more flood water through the structure at that time. But really what happened in the 1950s is what we were rehabilitating throughout the past several years. So over since that time in the 1950s, the outlet structure really hasn't changed that much. The state took over ownership of the dam in the late 1960s. One thing I do like to highlight, even though we have 207 dams that we are responsible for now, in the early 1900s, the state of New Hampshire didn't own any of the dams. Once again, this goes back to a lot of these power companies no longer needing these structures, such as Goose Pond Dam, that was transferred from the Granite State Electric Company to the state of New Hampshire in the late 1960s. 1980s, more drain lines were installed to relieve some of the seepage that was occurring at that structure. In the 1990s, we in-house, with that same in-house construction crew, actually did some work on the intake structure. This is the same structure that was present in the 1950s. Really, the big thing that they did in the 1990s was they drew down the impoundment to replace these flood control gates on the upstream side. These are actually all wooden boards that are stacked up on top of one another. And interesting thing, you'll see in the rehabilitation that these gates are no longer used at this site, but you'll see later on they actually got moved somewhere else. 2012, we were doing some repairs to the outlet tunnel. So basically those discharge gates discharge water into a tunnel. And while that work was taking place, we actually discovered some pretty significant leakage going on around that concrete structure. So once again, we know that the dam has historically had seepage issues through the earth embankment, but now we're actually seeing some additional issues around the concrete structure. So we did some additional borings within the actual embankment and discovered that water levels within the embankment were actually very high and that the soils were relatively soft as well. So that raised some concern. So in 2018, we did what they call a potential failure modes analysis. This is where everybody that's familiar with the dam, along with a consultant, sit in a room and really kind of dive in over a course of a couple of days. What could the issues be with this structure? What should we be most concerned about? And really what we found was that seepage along the abutments of the outlet works could lead to a failure of the dam, or seepage beneath that concrete core wall could also lead to a failure of the dam. So those are kind of the two biggest items that we really had to focus on. So what do? We do some more investigation. So in 2018, we did a whole nother series of borings, really trying to make sure we understood what was in the dam and what we were seeing in those 2013 test boring results. So they're actually drilling into the soils to figure out what's there. And you can see we also did inspections of those drains from the 1920s and the 1980s and found that a lot of those drains are actually compromised and no longer working efficiently. So what did we actually see? My apologies here, but I'm going to try to get this video working. One thing that we found, so it's actually having some issues playing the media, so I apologize for that. But what we found was artesian water pressures. So in this video, there's actually water dripping out of this case coming down. And so what that means is water is percolating up through the pipe on the inside of this orange box and actually bubbling out through the bottom of the box. We actually had to drill a couple holes to allow the water to escape. So the pressures below the dam were such that we were concerned that essentially erosion from internally in the dam where it could actually lead to a failure of the dam. So how do we go about addressing that? We started doing a full reconstruction design in 2020, which included rehabbing all of that concrete work and then also addressing the downstream side of the dam as well. Let me just jump back to my pointer here. So we started basically the downstream side, that was to address water moving through the dam, and the upstream side was to address concrete deterioration, along with addressing those wooden gates. Those wooden gates that were installed in the 90s actually had been underwater for over nearly 40 years. And so we were concerned about failure of those gates after that time as well. And just for context, this is the normal pond surface right here at the blue line that Goose Pond is typically at. And so to do this level of work, we had to draw down the pond roughly about 20 feet. Here's a little bit more of that seepage collection gallery that we installed, along with 20 different relief wells. So these wells were installed along the toe of the dam to collect that water moving through and to bring it down into the outlet channel so that we were reducing those pressures that we were seeing in those wells. Like I said before, in order to actually do this work, we had to drain Goose Pond down. This is Goose Pond drained down about 20 feet. Once again, a lot of these ponds are great ponds in their natural state. So it was a natural pond at one time. However, with the dam being there, it would artificially raise that impoundment. And the reason it was artificially raised is they wanted to be able to use that storage for downstream mill purposes. And so that's why a lot of the lakes and ponds that we enjoy all throughout the state are what we call raised by damming. There is a dam at the outlet of the pond because at one time someone was trying to use that additional water that was stored behind that dam in that body of water for downstream purposes. So the drawdown started in 2023 and construction started in 2024. The first thing we had to do is install a cofferdam. So everybody thinks you install a cofferdam, the pond can stay intact. That is typically not the case, but the contractor still has to be able to manage storm events. So in the case of Goose Pond, this 10 to 12 foot tall sandbag cofferdam was installed, and you can see this pump right here for context. That pump is about 5.5 feet tall. So this was installed to help allow for fluctuation during different storm events and make sure that we're not flooding out the construction site or even worse, causing an issue to the dam when it's under construction. So one of the things that we discovered early on, bear in mind that this dam hasn't been drained down since 1990, was that the outlet gates, we originally thought that these could be rehabilitated in place. However, we found that they were beyond their useful life and really needed to be replaced. So right off the bat, that was working with the contractor on implementing that change order to actually replace those gates. You can see the same configuration here in the 1918 as we see here. So those gates were actually over 100 years old when we finally removed them in 2024. These are the bypass pipes. So we actually had two 12-inch pipes that were running through the tunnel. So the workers were working around that. And this is the tunnel being relined with shotcrete in 2024 as part of that project, rehabilitating that concrete all throughout the structure. Some more concrete work taking place. These are basically refacing those concrete walls. This is where the gate was that has now been removed and new gates are going to be installed. And then those big wooden gates, we were concerned about a failure of one of those gates. It wouldn't necessarily be a dam failure, but it would certainly discharge a volume of water that could cause downstream harm. It would also lead to the loss of the impoundment. So we elected to actually remove those gates. We actually don't need them for flood control purposes, and rather actually install a much smaller operational gate for routine operations. You can see here, these are the drain lines going in. This happened basically in 2024 into 2025. And each one of these white pipes are actually those relief wells that are installed along this drain line. So the prior drain lines, those were all excavated and removed. and these new lines were installed much, much deeper, with one line collecting water from all these wells and the other line collecting any water moving through the earth. This kind of puts into context a little bit more, basically how these relief wells tie into a what we call a header pipe, and then another pipe that actually gets installed to collect water moving through. Once again, here's that red barn that you saw in the 1920s, and the drain line is pretty much in the same location, but it helps kind of put things in context how deep we had to go. So as we were wrapping things up in 2025, the contractor had installed the new gates. And because of that, we could no longer bypass water through the structure. So they actually had two 12-inch pumps on site to pump water around the dam. However, a lot of people think, oh, two 12-inch pumps, you should be able to move a lot of water with that. Unfortunately, you really cannot. So pumps are kind of a last resort when it comes to actually bypassing water. And unfortunately, in this case, we actually overtopped the cofferdam during storm events in the spring of 2025, simply because the pumps couldn't keep up. These are in the 2025, as we were regrading and kind of wrapping things up. You can see all those different wells now have a casing on it. One thing to note is that those drain lines, even during the refill process, were already working. You can see water coming out of this line right here. And so those drain lines exiting the walls were already working as we were refilling the lake. So unfortunately, we found during the summer of last year that the new gates actually had some issues. So last fall, we actually drew the pond back down after partially refilling it, did what we could to address the gates. We thought we addressed all the issues at that time. However, during final gate testing, we had to let the pond naturally refill back up to test those gates under full pressure. We found that there were manufacturer defects within these two low-level gates. And so right now we're working with the contractor and the gate manufacturer to come up with a repair procedure for those gates. So how much did this all cost? About $1 million for all the design and drilling work, about 6.5 for the construction. That was, unfortunately for us, mostly funded through the American Rescue Plan Act, basically those COVID relief funds that came in through the state. We're able to use that for reconstruction. It's also interesting, in 2020, the project was estimated at 3.4, so about 50% less than ultimately what the bids actually came in at. And the construction oversight for this project is about $1 million. So about $8.5 million, with the state funding about $1 million of that for reconstruction of Goose Pond. Now I'm going to jump up north, up to Murphy Dam. This is that dam that you saw originally in the original slide. Built actually by the state of New Hampshire. This is the largest dam that we have, and certainly largest dam ever built by the state. Built between 1937 and 1940, really for flood control purposes on the Connecticut River and to support downstream industry. Hydropower, water needs, things of that nature. It's a very big site. This is the main dam right here. We have the Broom Gate. That was that tower you saw in the original figure that discharges water to a control building. And then we have a big spillway over here, basically for storm events. Interesting thing to note, in 1939, it cost about $2.3 million to build this structure. In today's dollars, that would be about $55 million. This kind of breaks down the original location of the Connecticut River, and now we have Lake Francis. And so once again, here's the dam, here's that penstock, dowel valves. So the dam being just over about 100 feet tall, 2,200 feet long. The spillway is about 200 feet wide. And at the end of this 13-foot diameter penstock are two 7-foot diameter dowel valves. So all the water in the upper Connecticut basin goes through Second Connecticut Lake, First Connecticut Lake, then down into Lake Francis and Murphy Dam. So all the Connecticut River through Pittsburgh and Clarksville move through Murphy Dam. And that dam actually gets drawn down a lot for power purposes and flood control purposes. So here's the normal curve. You can see during the winter months, it actually drops anywhere from 15 to 25 feet to provide that flood storage and to continue to use that water for downstream purposes. So nearly 1 million cubic yards of fill was used to actually build this earth embankment, that fill being taken all kind of throughout the Pittsburgh and Clarksville area. It's kind of your typical earth embankment dam. with an impervious core, basically the center of that dam being tight material that water can't get through, and drainage material on the outside of that core so that if water does get in there, the material doesn't erode from inside out. Here's those three gates that were actually from Goose Pond. So here's up at the spillway. We have all these stop logs and these drop stanchions, and you'll hear a little bit more. In order to actually discharge water and be able to control that discharge to the spillway, particularly when the penstock is inoperable, we actually elected, because we were rehabbing Goose Pond, we took those three big gates and actually brought them up here to Lake Francis and installed them in the spillway. Here's some photos of actually that penstock that moves through the dam, 13 feet in diameter, and actually breaks down into these two valves that you can see here. These are those two 7-foot diameter valves. This is the inlet, which is under about 90 feet of water in Lake Francis, and then moves through this pipe. This is it exposed, and then discharges into these two dowel valves. These are those valves from the downstream side. Here's a photo of those valves actually being installed. And so once again, the whole Connecticut River actually moves through these two valves. And you can see here, here's over the course of a year, basically how we manipulate the river flow based on different needs, whether it's flood control needs or downstream hydropower needs. Because this is one of those sites that actually gets partially funded by the revenue generated from the discharge of water coming out of this facility. So, having it be a 90-year-old structure, we weren't quite sure what was the issues up here. So this is where we dove into a potential failure modes analysis. Once again, just like at Goose Pond, in 2018, we looked at what are the real concerns here. And really, those concerns focus on the spillway. You have 100-year-old concrete up there, and the fact that that spillway is prone to big ice loading during the winter season, along with flood loading, if there ever is a flood event up there. So certainly concrete deterioration is a concern. And those big steel stanchions, those are also of a concern if any of those stanchions actually let go, particularly when the pond is completely full, because there's about 15 feet of water behind all those steel stanchions. The PFMA also, though, highlighted the need and the importance of maintaining the dowel valves for control of the reservoir. If we lose those valves, we lose control of the Connecticut River downstream. And so we actually elected to look more into the valves. While we still need to be focused on the spillway eventually, we felt that the valves really need to be looked at because of their age and because of ongoing maintenance issues at those valves. So in 2022, we had a consultant look at the valves who really came up with a recommendation that said, within the next 2 to 4 years, you really got to replace those valves. They're at end of life, and they're certainly going to start causing issues. And some of those issues we've also actually seen over the past decade or two. So what exactly are some of the issues that we're seeing at those dowel valves? Basically, because the flows are and the pressures are so high, once again, these valves are holding back 90 feet of water that over time, basically the steel has been eroded out from the flow of the water. So the valves knock, they're basically loose inside their housings. And so there are issues when we try to go to higher flows over 400 cubic feet per second, in which things really start banging around pretty good. And that's because of steel loss, not only on the plates of the valves themselves, but also in the operators that raise and lower those valves and basically manipulate the openings. So we dove into an alternatives analysis. What are our alternatives for replacing these valves? Do nothing and continue what we've been doing. However, those valves are certainly at the end of the life, all the way up to actually trying to replace both of those valves. We chose to go with option 4, which was actually replacing both of those valves, with the idea being, well, we always can step back if we need to and just replace one, but let's see if we can't actually try to replace 2. So we had a consultant develop design plans for that. And the thing with the dowel valves up there in the Connecticut River is downstream of Murphy Dam is one of the best fisheries in the state for cold water fish. The reason is that water is 90 feet down as it's being discharged. So it's very, very cold, typically well below 50 degrees. And so the benefit of that is that cold water coming out provides that cold water fishery. So we collected a lot of data to figure out when can we shut down the penstock discharge to the spillway, knowing that at certain times of year, the water is going to be warmer out of the spillway. So what can we do? These are the two new valves that are likely going to be installed. And really, basically, we're installing those downstream of the existing dowel valves. So if during construction we still have to operate those dowel valves, we can. So say the contractor has to demobilize because water temperatures get too great, we can discharge from the bottom of the lake, allow water to move out, and then once these new valves become operable, then we can fully remove the old valves. So how is this all going to work? Well, we actually put this project out to bid and we're reviewing bids right now. But really, the shutdown periods, because of the water temperatures, is we're going to have to shut down the penstock about October 1st. Based on that 2025 data, it looks like October 1st we can shut down and have cold enough water in the spillway through those 3 gates that we installed from Goose Pond, discharge water from October 1st to January 1st. At that time, because of the downstream needs, the water level actually drops below the spillway. So then we have to start releasing through the penstock once again through the winter months. However, with the spring runoff, the water in the lake comes back up. We can discharge through the spillway, shut down the penstock for a couple of months until June when the temperatures become too great. So over the next several years, it's going to be kind of an on again, off again as we try to get this project done by shutting down the penstock for a period of time, allowing water to go through the spillway, and then opening it back up. So that is one of actually the biggest challenges that we face with this project. And you can see here, this is exactly that. That's that blue line. So that is the bottom of the spillway. And so when this average lake level line is above that, we can discharge to the spillway as long as the temperatures are appropriate. However, when the water elevation drops below that spillway, we have to discharge to the penstock. Otherwise, there would be no flow in the Connecticut River. So this goes back to 2018 when we dove into that PFMA analysis. So it was about $50,000 to do that analysis. However, there was a lot of different steps that we had to do in between. So that assessment to look at the dowel valves in 2022 was almost $500,000 because what we found in order to shut down the penstock appropriately, there were issues with the gate that is actually located in the tower that you saw at the beginning of my presentation. So we had to address those issues at the gate up there in order to shut down the penstock to do the evaluation. So that was about $500,000 to move those gates from Goose Pond and install them up on the spillway at Murphy Dam. That was about $162,000 for all that work. We also needed to upgrade the electrical services coming into where those dowel valves currently operate. So that was almost another $500,000, basically running all new electrical service from the utility all the way to the building. Because once again, everything that was in the ground was direct buried from the 1930s. So all of it needed to be replaced. We then dove into the alternatives analysis and the design, almost $400,000 in that. And you'll see, just like the Goose Pond project, once we get into 2023, we were able to use a lot of ARPA funds to do those different designs. Construction oversight is going to be almost $600,000 for the new jet valves when they go to get installed. And that's oversight by our design engineer to make sure everything gets done properly. That's going to be done using capital funds. We no longer have the benefit of the ARPA funds. So now we're looking at using the state funds to do that. And the construction and installation of the jet valves to replace those dowel valves is roughly about $7 million. So, and that's being funded partially by those water user funds for the downstream hydro, but also state funds as well. The interesting thing to note is each valve is about $1.4 million. So just to replace the dowel valves up there at Murphy Dam, we're looking at about $9 million. Never mind what we have to do eventually to address the issues up at the spillway. So you can quickly see how that $300 million for 64 of these high hazard dams, we get to that number very, very quickly. And quite honestly, it's probably a little low than what we actually see because that averages out to about $5 million for each high hazard dam. So some of the issues that we see statewide, that we're going to have to address once we address these other structures. This is Lakeport Dam, outlet of Lake Winnipesaukee. We have gates, 3 big gates, 10 feet tall, about 18 feet wide, that were installed in 1958. And just like those dowel valves, we're seeing a lot of section loss and a lot of issues. So that is a project that we need to certainly address in the short term up on the outlet of Lake Winnipesaukee. Moving downstream, Lake Winnisquam, that dam is still founded on timbers from the 1800s. And so certainly when you look at the criteria for sliding and overturning and basically what this dam would do during a design event, it's likely not going to pass, certainly looking at the new modeling methods. And so that dam will also have to be addressed as well. Moving over to Squam Lake. Squam Lake, we know that that dam being a high hazard dam certainly does not have the ability to discharge a 1,000-year storm event. And to be perfectly honest, a 1,000-year storm event here in New Hampshire, somewhere around 10 to 12 inches of rain in a 24-hour period. And if anybody's been paying attention to what's been happening in Albany, New York over the past 24 hours has received over 10 inches of rain. So it's not out of the question that New Hampshire is not going to see something like this in the future. And even over at Lake Sunapee, there's certainly a lot of concrete section loss. And although that dam is much smaller, those piers are certainly deteriorated and eventually going to need to be rehabilitated. And then down at Pawtuckaway Lake, this is one of the more concerning issues that we're dealing with right now. Pawtuckaway Lake is actually impounded by 4 dams, but on the biggest dam on Pawtuckaway Lake is, while the leakage that you see here is very historic, we've seen that leakage moving through the dam is actually now starting to pull material from the dam itself. And so we're seeing sinkholes like this actually being created as a result of the material actually moving through the dam. And so that's a project we're actually trying to use existing funds to get the design done, and then actually trying to get creative and looking at some different grant funding opportunities, because the rehabilitation of all 4 Pawtuckaway Lake structures is actually going to be about $20 million. Once again, averaging out to about $5 million a structure. So this is the maintenance and repair life cycle. And so this is for not just state-owned dams, but all dams throughout the state. First, you have to understand what you're working with. Identify the known historical issues through inspections and documentation. All dams in the state, certainly all hazardous dams, are inspected on a routine basis, hopefully by the owner, but also by the dam safety program. So we have those inspections going back decades and decades. So you can get a good understanding of what you're dealing with. However, there's always unknowns associated with all of these structures. They're just like an old house. The minute you start diving into the wall of an old house, you're going to find things you didn't know that were there. So determine the gaps through a potential failure modes analysis. As you saw, we did one on Goose Pond, we did one on Murphy Dam as well, and we're continuing to do those throughout the state to really dive into what we know and what we don't know. And then what additional studies that we have to do? Do we have to do additional test borings out there? Do we have to do additional modeling to really figure out, is this dam compliant or not? And if it does need to be rehabilitated, look at the alternatives. Can you do nothing? Can you do something simple? Or is it completely removal of the dam and reconstruction of the dam? With that being said, ultimately looking at the financial implications and the long-term maintenance costs, simply removing the dam, is that the better alternative moving forward? Yes, it does impact that water resource, but the benefits of restoration, such as aquatic organism passage by the dam not being there, may actually outweigh having that open body of water behind the dam, and ultimately actually be much less costly because the removal costs are much lower than the rehabilitation costs. Once you select the alternative, you got to go through historical reviews, get the necessary permits, and finalize your design. So even once you figure out which way you want to go, there's a lot of work to be done just so you can get a shovel-ready project that you can then move into construction. In that construction project process, just like I said at Goose Pond, you're going to run into unknowns during that. So you got to make sure you have contingency funding in there allocated for those unknowns as they crop up during construction. So with each step is you have to understand the funding needs for each step. So a lot of times here at the state is we'll request funding to try to get the first couple of steps. Then once we know what direction we'll go, we'll get additional funding for that design step until finally we get the funding for the construction step. Kicking things off, it's really difficult to understand just how much these things are going to cost until you really start diving into the weeds. So with that, that's kind of my soup to nuts presentation, a couple of case studies on dam rehabilitation projects that are ongoing here in New Hampshire, along with some of the challenges that we have, and then also an overview of the Dam Bureau. So thank you for attending tonight, and certainly I'll open it up to questions, but if you have any other questions that aren't answered tonight, my contact information is here.
Yes, thank you so much, Corey. I have to say, this is probably the fourth time I've heard you talk in over 2 years, and I learn something every time. I'm over here writing notes. I have like sticky notes in front of me, just in front of my desk. So, with the 4 minutes that we have left, we're gonna answer or ask some kind of general questions, and then if you have anything, like Corey just said, if you have anything that we don't answer, you have his contact info. He's opening himself up for you to send him an email or give him a call. So the first one let's address for the water quality and precipitation data that is collected at these dams. What is that data used for?
So most of the time, the precipitation data is used for our forecasting tools. So that website I showed earlier, here at DES, we actually have a whole nother interface that is not available to the public, where we can actually using that rainfall data along with other data inputs through NOAA and other federal agencies, weather agencies, we can actually predict what is going to happen on a particular water body. Not all water bodies, but the ones that we have modeled in within the forecast. So, for example, Lake Winnipesaukee, we certainly have that modeled. So based on the rainfall forecast that we've been seeing over the past 24 hours, we've been monitoring what we think is going to happen out of Lake Winnipesaukee. And then as it starts raining, those forecasts are adjusted based on the actual rain that's occurring. Because once again, you have water that lands up in the watershed. That's going to impact the water body when it reaches the water body. So that's typically where that precipitation data gets used.
Sure. So if someone, thank you, if someone notices that the loggers aren't working or something seems off about the data that's coming through, should they be contacting you? Should they be contacting someone else?
They can certainly contact us. I mean, we monitor it daily. I will say there are some sites on that website that we know are down and not functional at this time. Fortunately, when it comes to the precipitation data, and there's a lot of redundancy and backup. So just because we're not getting precipitation data at a particular site, there's other tools, like I said, through NOAA forecasting, radar tools, and other things that we can get a pretty good understanding of what's happening in that watershed.
Wonderful. And uh, another question we have with all of the aging dams, how do you decide which one to fix, especially with all of the money that you have?
Right, right. So we have a capital appropriation request in now for about $16 million. And really it's focusing on things such as the Lakeport gates, but also there's also small dams throughout the state that may not be hazardous, but have a really big economic impact, such as like Back Lake Dam up in Pittsburgh, low hazard dam that has to be fixed. And so it's kind of balancing those economic impacts with the low hazards along with the risk borne by having some of these high hazard structures. So we do have an asset management program that we're constantly trying to update and develop, and that's kind of in the works and coming together, that really hones in on, helps us make these decisions on what we need to actually address moving forward.
Okay. I think we have half a minute left. How does climate change impact our dams in New Hampshire and impacting your work in New Hampshire?
So climate change is one, probably the most
Big question for 30
significant
seconds.
impact that we're seeing is that the precipitation is increasing all throughout the Northeast. And we're seeing that in design data that's coming out of NOAA that we have to use to design these structures. The interesting thing is that increase in precipitation is from more frequent heavy events. Like I just mentioned, what's happening in Albany, 10 inches of rain. We had almost 7 inches of rain in the Madison area just a few months ago. Now, this past month, it's been bone dry with very, very little rain. So it's either all on or all off. And from a lake management perspective, that's very difficult, particularly when you're trying to manage these lakes for recreational purposes. So what we're trying to do is do things conservatively, maybe run a lake a little bit higher, try to store that additional rain when it comes in, knowing that typically in the summer, things are going to drop off. And certainly that's what we saw this past year. And that's what we're seeing right now is things are really, really starting to dry up. And so it's it's more severe events, more severe precipitation events, and more severe dry events. That's kind of what we're seeing. And so that really creates a challenge on trying to maintain not only lake levels, but also trying to maintain downstream river discharges as well for the ecological benefit that they provide.
Thank you, Corey. That was our last question of the evening. We're actually a minute over, so we didn't get to a lot of questions. So please definitely reach out to us, reach out to Corey with any questions that you have that we can all help answer. And again, last thank you to Corey for coming out tonight and joining us on this webinar. And we all hope you have a great night.
Thank you, everyone.